Bonding and structure. The chemical and physical properties of substances depend on the underlying bonding and structure of the compound. Bonding types are metallic, the electrostatic force of attraction between positively charged ions and delocalized electrons. Covalent, the electrostatic force of attraction between positively charged nuclei and negatively charged shared electrons. Ionic, the electrostatic force of attraction between positively and negatively charged ions. Types of structure are metallic, a giant lattice of positively charged ions and delocalized electrons. Covalent molecular, discrete molecules held together by weak intermolecular forces. Covalent network, a giant lattice of covalently bonded atoms. Ionic, a giant lattice of oppositely charged ions. Monatomic, discrete atoms held together by weak intermolecular forces. The first 20 elements in the periodic table can be categorized according to bonding and structure: metallic, lithium, beryllium, sodium, magnesium, aluminium, potassium, calcium. Covalent molecular: hydrogen, nitrogen, oxygen, fluorine, chlorine, phosphorus, sulfur, carbon. Fullerenes. Covalent network: boron, silicon, carbon, diamond and graphite. Monatomic: helium, neon, argon. The type of bonding in a compound is related to the positions of its constituent elements in the periodic table. Compounds each adopt one of three structures in the solid state: covalent molecular, covalent network, including silicon dioxide and silicon carbide, ionic. Intermolecular forces of attraction. Van der Waals forces are the result of electrostatic attractions between temporary dipoles and induced dipoles caused by movement of electrons in atoms and molecules. These weak forces operate between all atoms and molecules and are much weaker than all other types of bonding. The strength of van der Waals forces of attraction is related to the size of atoms and molecules. Although weak, van der Waals forces are related to the properties of atoms and molecules, where these are the only intermolecular forces present. Differences in electronegativity give an indication of the polarity of a particular bond. A covalent molecule is said to be polar if it has a permanent dipole. Polar covalent bonds occur when the atoms of the bond attract the bonding electrons unequally, causing the atoms to have partial positive and negative charges. The polarity of a covalent bond depends on the difference in electronegativity between the bonded atoms, the most electronegative becoming more negative. The spatial arrangement of polar covalent bonds present is important in determining molecular polarity. Molecules with polar bonds which are not symmetrical have a permanent slight positive, delta positive, at one side and a slight negative, delta negative, at the other. These molecules are said to be polar molecules. In symmetrical molecules with polar bonds, the charge is distributed such that positive and negative charges cancel out. These molecules have no overall dipole and so are non-polar. Molecules which are polar have permanent dipoles, and in these substances there are permanent dipole interactions. These are electrostatic forces of attraction which occur in polar molecules in addition to van der Waals forces, and are stronger than these forces for molecules of equivalent size. Hydrogen bonds are permanent dipole interactions. Molecules containing a hydrogen atom bonded to an atom of a strongly electronegative element such as fluorine, oxygen or nitrogen are highly polar, and the forces of attraction between these molecules and a small, highly electronegative atom on a neighbouring molecule are called hydrogen bonds. Hydrogen bonds are stronger than van der Waals forces and also stronger than other forms of permanent dipole interaction, but are weaker than covalent bonds. Properties of elements and compounds. The structure and bonding in elements and compounds governs how the substance behaves in terms of its physical and chemical properties. Melting point, boiling point and hardness or softness, solubility in polar and non-polar solvents, viscosity and miscibility with water are all properties which depend upon and can be explained by a knowledge of the structure and bonding. Ionic compounds and polar molecular compounds tend to be soluble in polar solvents such as water and insoluble in non-polar solvents. Non-polar molecular substances tend to be soluble in non-polar solvents and insoluble in polar solvents. Anomalous patterns in properties of substances can sometimes be explained in terms of their bonding and structure. Boiling points of ammonia, water and hydrogen fluoride can be explained in terms of their hydrogen bonding. Hydrogen bonding between molecules in ice results in an expanded structure which causes the density of ice to be less than that of water at low temperatures. Uses of diamond, graphite and silicon carbide are related to their structures and properties. Fullerenes, large molecules containing carbon atoms, are the subject of current research and uses are being sought. The mole. 1 mole of any substance is the formula mass of the substance expressed in grams, the gram formula mass, GFM. 1 mole of any substance contains 6.02 times 10 to the power of 23 formula units. A formula unit may be an atom, a molecule, or a group of atoms or ions, depending on the structure of the substance. 6.02 times 10 to the power of 23 moles per litre is known as Avogadro's constant and is given the symbol L. Equimolar quantities of substances contain equal numbers of formula units. Calculations can be carried out involving the interconversion of masses of substances and number of particles. The molar volume is defined as the volume occupied by 1 mole of a substance and is quoted in units of moles per litre. The volume of a gas varies as the temperature and pressure change. The molar volume is the same for all gases at the same temperature and pressure. The molar volume can be calculated from the density of a gas. The volume of a gas can be calculated from the number of moles and vice versa. The volumes of reactant and product gases can be calculated from the number of moles of a reactant or product via a balanced equation. Prescribed practical activities for Unit 1. Investigating reaction rate and concentration. Aim: to investigate the effect of changing concentration on the rate of reaction between hydrogen peroxide and acidified potassium iodide. Method: different concentrations of iodide ions are added to hydrogen peroxide solution. The reaction is followed by including a small amount of starch and sodium thiosulfate in the mixture. The iodine produced reacts with the thiosulfate, and only when this has been used up will the excess iodine turn the mixture black. This is called a clock reaction, as we are timing it to the point where the same amount of product has been formed. Results: as the concentration increases, the rate increases proportionally, i.e. double the concentration and you double the rate. Conclusion: for many reactions, the rate is directly proportional to the concentrations of the reactants. The faster reaction rate is due to the increased number of collisions, which must occur with higher concentrations of reactants. Investigating reaction rate and temperature. Aim: to investigate the effects of changing temperature on the rate of reaction between oxalic acid and acidified potassium permanganate. Method: measured volumes of oxalic acid and permanganate solution are added together. Initially the mixture is purple due to the permanganate ions, but this colour slowly fades as the reaction takes place. The reaction is timed to the point where the colour completely disappears. The experiment is then repeated at different temperatures while keeping the concentrations and total volume of solution constant. Results: as the temperature increases, there is a marked increase in rate. Conclusion: a small rise in temperature can lead to a large increase in reaction rate. This is due to two factors. Firstly, at the higher temperatures, more collisions occur as the particles move about more quickly. And secondly, more particles will have the activation energy needed to react when they collide. Enthalpy of combustion of an alcohol by experiment. Aim: to find the enthalpy of combustion of ethanol. Method: an alcohol burner containing ethanol is used to heat a beaker of water with a thermometer in it. The following measurements are made: mass of water, temperature of water at start, temperature of water at finish, mass of burner plus ethanol at start, mass of burner plus ethanol at finish. Results: The enthalpy of combustion of ethanol is calculated using the equation energy change is equal to Cm delta T, where C equals specific heat capacity of water, 4.18 kilojoules per kilogram per degree centigrade, M equals mass of water, kilojoules. Delta T equals change in temperature of the water. Experimental error. The values of enthalpies of combustion found by experiment will always be lower than they should be. This is due to heat loss to the surroundings.